Hi, I'm Maha. I'm going to explain about separation train for 1,3-butadiene production. 1,3-butadiene can be produced through acetylene co-product process, Henry process, and OXD process. Separation train for all the three processes are shown in the following table. Three components are to be separated in all the three processes. So, two separators are required to separate three components. In route A, which is acetylene co-product process, three components that to be separated are C3-acetylene, 1,2-butadiene and 1,3-butadiene. In Henry process, which is route B, three components to be separated are propane, butane, and 1,3-butadiene. In OXD process, which is route C, crude butadiene, waste, and light carbon are the three components to be separated. Cost analysis was also performed. Cost analysis was only applied on main equipments. Cost for cost analysis were obtained from Alibaba.com. For route A, the cost of equipment is $260,000, while for route B is $325,000, and for C, which is OXD process, the cost of equipment is $240,000. Thank you.
The next section will be catadiene process, which is route B. There will be three different types of heuristic that can be categorized in this route. First of all is heuristic number 4. Introduce purge stream to provide stream for exit species. It can be noted that the exit species from the adsorber, stripper, and the depropanizer will be expelled once the reaction has completed. Next is heuristic number 6. Recycle to extinction. However, it can be seen that the higher byproducts is being produced through this process, which is completely undesired. Next will be heuristic number 7. Competing parallel reaction, therefore the temperature and the pressure should be adjusted to produce higher yield. However, through this process, it can be noted that the yield of butadiene produced is much lower comparing with the route number A.
Hi, my name is Dibutadiene, and I'm going to continue the presentation on revision of the PFD based on separation train synthesis of route C. The route C, which is the oxidative dehydrogenation of N-butane, which is known as OXD process. I'm going to explain 4 heuristic rules for this process. As you can see from the route C PFD, which is I put in the slide, first rule is heuristic 1, which is the avoid or reduce the handling and storage of the hazardous and the toxic chemicals. This heuristic 1 can be applied in our process due to there is no toxic handling in this process. The second process is heuristic 4. Heuristic 4, which is introducing the liquid or vapor purge stream to provide exit for species. So in our process, this heuristic 4 is applied because of the usage of the separator and distillation column. We let the effluent product to purge off from the stream inside the process. Okay, thirdly is heuristic 9, which is the separate liquid mixture using the distillation and stripping tower and also liquid extractor among similar operations. This as heuristic 9 also can be applied in our process because due to the presence of the distillations column that separate the liquid mixture in the process. Lastly is heuristic 16, which is to increase the pressure of the stream, pump a liquid rather than compressing a gas. This process, this heuristic is applied in our process because we replace the compressor into a pump, which also will be include our cooler and also heater to the process. Okay, that's it from me. Thank you.
Hi, my name is Mirise and I'll be presenting on the process optimization in the production of 1,3-butadiene. First of all, before I go in depth in explaining the criteria that we have proposed in the process optimization approach, I would like to briefly explain that there are two approaches that can be used. First is the parametric optimization approach, and the next will be topological optimization approach. Parametric approach focuses on the design variables such as temperature, pressure, reflux ratio, and etc. However, for the topology approach, it focuses on the overall process flow diagram as well as the arrangement of the equipments. In order to upgrade the existing oxidative dehydrogenation process, topological optimization approach is chosen by my group. The three criteria that we have examined is the elimination of unwanted byproduct. In this case, it is the formation of carbon dioxide, rearrangement of equipment, as well as the alternative separation methods to be used. Based on this process, the exothermic reaction taking place at the reactor generates heat that contributes to high temperature rise. At high temperature rise, oxygen reacts in the feed stream to produce carbon dioxide, which is the undesired byproducts. Carbon dioxide doesn't have a great value, or it is not advisable to be sold. So this formation of carbon dioxide affects the yield and selectivity of the desired product that we want, which is 1,3-butadiene. So in order to reduce the temperature rise or to recover the heat that is generated or evolved in the reactor effluent, we have decided to add steam. Although addition of steam may require some expenses, we need it in a very minimal consumption. As explained by one of my members in the study of feasibility, the advantages of this process is that it uses low steam consumption. Not only that, addition of steam also initiates high selectivity of 93% of butadiene with a percent conversion of 65% of normal butene. Therefore, the temperature rise can be minimized and we have achieved our objective of having a high selectivity and yield of the product itself. Next, instead of using a compressor to compress a gas, we use pump to pump a liquid instead, as it is much more efficient. The arrangement of the pump is illustrated in the process flow diagram that is attached in the slide itself. And lastly, in terms of alternative separation methods, the original process flow diagram consists of a combination column which comprises of absorber, degasser, and stripper column to separate crude butadiene from its impurity. Here, to reduce the complexity of the process flow diagram, we chose to use a separator and distillation column instead to produce 1,3-butadiene at the distillate as well as to eliminate the impurities. So that's all from me, and thank you.
Hi, my name is Helena Francis and I'm presenting the conclusion. A process to manufacture butadiene should consist of the following design characteristics: A. Low steam consumption and heat energy consumption. B. High conversion and selectivity per reactor cycle. And C. Longer span of the catalyst. The oxidative dehydrogenation of N-butene satisfy the following criteria because It requires low steam and heat energy consumption. It has a high conversion of approximately 65% and a selectivity of 93% per cycle. And C, its catalyst has a long lifespan and does not require frequent regeneration. The oxidative dehydrogenation of N-butene is chosen in comparison to steam cracking of paraffinic hydrocarbon simply because the steam cracking of paraffinic hydrocarbon is a complicated process and it is a costly process. It requires a variety of feedstock. Also, it makes use of toxic chemicals and it produces high impurities from the crude butadiene distillation process. The Howdy process or Route B is not chosen as the best process to produce butadiene because of its low yield and high process cost. Also because it produces a large amount of coke as a byproduct in its process. Route C, or the oxidative dehydrogenation of N-butene, is the best route for the production of butadiene simply because it has the safest feedstock, it has a low process cost, it has a high conversion rate and selectivity, and at the same time requires a low amount of heat energy. With that being said, ODH, or oxidative dehydrogenation of N-butene, could reduce costs and save energy. Capital and operational efficiencies are gained by eliminating shutdowns due to decoking processes, and also because they could conduct fewer maintenance operations because of the lack of premature shutdowns due to decoking process. So therefore, in conclusion, it can be said that the oxidative dehydrogenation of N-butene, which is studied throughout this assignment, is the best method that can be used to produce butadiene in the industry. The main reasons being that this process consumes less amount of energy compared to the other two processes, resulting in a lower cost. The raw materials used are also cheaper than those in other processes. Also, there are fewer unit operations, which means that the production of butadiene requires lesser energy, which obviously contributes to a lower cost. The fact that the catalyst does not need regeneration is an added benefit. So with all the reasons given above, it can therefore be said that the production of butadiene via the oxidative dehydrogenation process is indeed the best method to produce butadiene in industry. Thank you.